Hey everyone, welcome back to another video. और आज की वीडियो में we're going to be talking about polar form and De Moivre's theorem, okay? Yeah, so I just figured that we should cover the topics and yeah. Okay guys, but before that I want to show the principal range of the quadrants when you find the argument. So I just wrote this down. This is quadrant 2, 1, 3 and 4, okay? No, pi upon 2 means 90 degrees, 180 degrees. This means 0 degrees, 90 degrees. This means negative 180 degrees, minus 90 degrees. Okay, and this means negative 90 degrees to 0 degrees again. Now this is because if we draw some points here, we can get I, 2I, 3I, okay? Negative 1, negative 2, negative 3, negative 4. So in this case, you can see in quadrant 2, it's going from 90 degrees, okay, to 180 degrees. Because the argument, yeah, one more thing, the argument of an imaginary number can either be on its positive real axis. This is the positive real axis. So the argument of an imaginary number on the positive axis will always be 90 degrees. So this, and the argument of a negative real number will be 180 degrees, okay? So that's something I want to explain as well. How to find the argument of pure imaginary numbers and pure real numbers, okay? First, we'll talk about that. Okay, this is the range. Now look. Similarly, we have 1, 2, 3, 4, 5, 6. Okay, look. I'll just start here. So minus 2i, minus 3i, minus 4i, minus 5i, minus 6i. Okay, look. Basically, to understand these principal ranges, just think when you find an argument. So in this case, the argument of an imaginary number on the positive imaginary axis is 90 degrees. Why? Because when we multiply by I, 90 degree rotation. We know that, right? Or we can say pi upon 2 radians. Okay? So either way, that's why it starts from the imaginary to the real. So first 90 degrees and multiplying by neg is a 180 degree rotation. And the reason multiplying by negative number gives a 180 degree rotation is because, like from 3, if you rotate 180 degrees, we land at negative 3. So we're just rotating to 180 degrees. And I explained this when I made a video on complex numbers about angle rotation, okay? So we can also think of the argument, okay? Yeah, one more thing. I think I should write it here though. Oh, it's right here, my eraser, okay? So, yeah. So here. So argument. Oh god. Alright. Argument can also be thought of as what? As how many degrees plus radians a number is rotated, gets rotated when we multiply . we multiply the number by it. So guys, I have another definition of argument. Now in my previous when I made the video on the argument on the whiteboard, I said that argument is determining what angle a complex number represents on the positive real axis. That's true, because the positive real axis is the standard way to express it. Like if we have any complex number, we can just represent it on the positive real axis, and we can find the argument. But we can also think of it as how many degrees a number gets rotated when we multiply that number by the original number. For example, I said that multiplying by I gives a 90-degree rotation. That's why it's going from 90 degrees. And also, one more thing, this 2 right here, or the 3, so the coefficients of I won't matter, because the coefficients of I, the real number coefficients of I is just a scaling factor. Like if I multiply 4i by 5, this means we get 20i. So this means 5 is being rotated 90 degrees, right? Or pi 1/2 radians. Okay? But 4 is just scaling it, because if you land on 4i, suppose this is 4i. If I multiply 4i by 5, we're still gonna stay on the positive imaginary axis, right? We're not going anywhere, right? 4i will still remain on this, because multiplying by a positive real number does not rotate the number. Yeah, multiplying any number by a positive real number just scales the number. Like for example, if you're on -3, if you multiply 3, we'll just land on -9. We're just scaling the number. We're just extending it. It's an extension. Okay? Yeah, and that's why. So that's why the coefficients don't matter, okay? That same goes with the negative real numbers. Multiplying. Now when we multiply, suppose 5 by -5. You can break this down into 5 into -1 into 5. So first think of this as this. This right here is a 180-degree rotation, or pi radian rotation, and we get -5. Now multiplied by 5 is a 0-degree rotation. No, I just wrote 0-degree rotation. Okay? Because when we multiply it by 5, we're just extending. We just extend the number line that we're on, whether it's the positive, negative, or the positive real axis, negative real axis, positive imaginary axis, or negative imaginary axis. When we multiply a positive number by it, after multiplying it by -1, there's no rotation. We're just extending where we are. But that's why we think of the main reason is multiplying by -1 rotated by 180 degrees. If you the coefficient of -1 will not matter, because we're just scaling it, so there will be no rotation. Okay? Yes. So that's how we can think of it as. Okay? So that's why this is the range. This is the range in which a complex number, would lie. Yeah. So whatever quadrant it belongs to, depending on the sign of the complex number, this will be its principal range, and it's helpful when we determine the argument. Okay? Okay, everyone. So now, yeah. So similarly, it goes from this. That we just when we're seeing the principal range, we're just going from the imaginary to the real, because rotating, we have to see how many degrees that number will rotate another number. Okay? Yeah. So it's like in quadrant 1, 0 degrees, because Because in this case, it'll be 0 to 90 degrees. Why? Because look, the thing is, multiplying, let's see, we have to go from the lowest to greatest value. So it's not just about starting from the imaginary then the real. We have to see, when we multiply by 1, when we multiply by a positive real number, there's no rotation, right? We agree on this? That's why it's 0. And pi upon 2, because as discussed, multiplying by I gives me 90-degree rotation. Good? So clear on these two? I good. Now come on quadrant 3. So negative pi, yeah. Now this is because we have this section, these sections in quadrant 3. Now look, the reason we're putting the negative, you think why? Let's see. You see this negative 180? Yeah. Well, what we're doing is, so look, there's a cool thing. Let's do 90 degrees, negative 90 degrees. 0, 0. 90, negative 90, 180. Like from here it's flipped. And 180, it's 90, negative 90. 0, 0, 90, negative 90. And the reason this is flipped from this one is because we have to go from the least to greatest value, right? And obviously minus 108 degrees is less than 90 degrees. So you have to start from negative 108 degrees. Understood? So this is how it works. Okay? Because like if we have, like suppose here, like if I have if I multiplying by negative I. And yes, as I said, the coefficient of, like for example, let's see, this is equal to, we can write this as negative 1 into I, right? And the coefficient of this whole thing does not matter because multiplying, like it'll just be a positive number, the coefficient. So if we have a coefficient like, if you have a coefficient here x, this will be a 0-degree rotation. Now this is because this will be a positive number when we split these two. Okay, good. Now look, multiplying by negative 1 is a 180-degree rotation, and plus multiplying by I, 90-degree rotation. And they'll go 270 degrees. But look, we want to put 270 degrees in the principal range. Now, we know that multiplying by, I meant rotating by negative 270 degrees is equal to rotating by positive 270 degrees is equal to rotating by 90 degrees. And you don't have to put the positive sign, I just put it. That's okay. Because look, you can test this, it's proven. Like, if I rotate a number, suppose I. So, let me rotate 270, let's rotate this 270 degrees. So, this means rotating, this means 90 degrees times 3, right? So, rotating this number 3 times. If you multiply this by I, you'll get negative 1. Now, if you multiply this by I again, you'll get negative I. And if you multiply negative 1 by I, you're going to get on 1. Now let's use the same method to multiply. Instead, we're going to multiply by negative 9 degrees. Now from our knowledge, we're rotating by 90 degrees, multiplying by I. So rotating by negative 90 degrees means multiplying by negative I. Yes. So when we multiply by negative I, we'll land on this. Same method. We're still going to land on 1 anyways. Understood? Okay. And now this one, last one, negative 90 degrees. Oh yeah, one more thing. Then, so yeah, that's why we put negative 90 degrees here, because it's greater. Now look, negative 180 degrees. Okay. So yeah, look, suppose like I have something here. Now look, the reason we're putting, one more good thing, the reason you're putting 180 degrees instead of putting, you might be asking, well, but why are you putting negative 180 degrees? Isn't rotating by 180 degrees equals rotating by negative 180 degrees? The answer to this is yes, this is correct. We can rotating by 180 degrees and negative 180 degrees is equal. Because, like multiplying, like for example, if you multiply any number by 1, okay, if I multiply a number y by 1, by negative 1, it will be 180 degrees. So if I multiply it by negative, that means I'm going to have to put double negative, right? Right? No. Because rotating by 1 degrees, rotating by, when we multiply any number by 1, this will cancel out. We'll just get positive 1. But that will be 0 degrees. But we can't say rotating by negative 180 degrees is equal to rotating 0 degrees. It doesn't make sense. Because rotating 360 degrees is equal to, or negative 360 degrees, or any multiple of that will give us equal to rotating 0 degrees. So that's why rotating by this is equal. Now we can try this. If you have a number I, let's take 2i. If I rotate this 180 degrees, I'm multiplying by my negative 1. So when I multiply this by negative 1, I'll get negative 2i. In the same way, if I multiply this by negative 180 degrees, I'm just switching the side from this side to this side. This is what's happening, okay? I'm just switching from this side to this side. There's no difference. We're still going to land on this, 2i. We're still going to land on 2i. Okay? So that's the goal. That's what's happening here, okay? Alright? Now, come here. Negative 90 degrees. So yeah, that's why we put one negative, because we can't put the same number here and here. Because then, if we do that, the arguments will be different. And yeah, I explained in my previous video when I talked about the argument that sometimes arguments are that the argument formula is different for each quadrant. So that's why I explained that we have to perform some operation to shift the quadrant of it so that the argument is equal. Okay, so that we represent the exact angle of what the complex number is. Now this is what we're doing here actually. So actually what's happening here is like that's the same thing. But the reason we're not gonna put positive 180 degrees because that'll be a whole mismatch, you know, and we don't want that to happen. So yeah, because when we're going down here, this will obviously be negative, right? If we're going from positive to negative. Because look, this is negative, this is negative. And this is positive, but this is negative. Okay? So like we can't say positive, okay, understood? Positive 180 degrees. We can't say that. Okay? Because obviously then the argument will be wrong. Okay? Now coming here to quadrant number 4, we have negative 5.2. This is negative 90 degrees. And from this range to this range. Okay? So we're going from negative 90 degrees to 0 degrees. So what this means is, like suppose I have a number, let's take it here, negative 90 degrees. Yeah, because look, multiplying by minus I equals rotating negative 90 or 270 degrees. But in this case, we can rotate 90 degrees or 270, but we're going to have to cancel the 270 degrees because we want the principal argument. This is the principal range, okay? So that's why I put negative 90 degrees here. It's pretty simple. And 0 degrees because, as explained, multiplying by a positive number scales the number, does not rotate the number. Alright? Oh god, yeah. So I hope you understood this. Okay? And this is just the range. So the principal range is what range the argument should be. The argument should be in the range of the principal range of the quadrant. Okay? So just a quick summary. For all the quadrants, principal range, let's do a brief summary. Okay? Now for quadrants 2, 1, 3, 4, IB. Ooh. Okay? So we're gonna put the principal range here. What is it? Yeah, negative 5 on 2. Yeah. So yeah. Yeah. So from pi 1, 2 to negative pi. Okay? And this is in radians. In radians. And the reason I'm putting in radians is because it's a standard rate. If you want, you can convert it into degrees. I'll show the formula how to convert it, but first understand this. The principal range, pi upon 2 to negative pi. This just basically means, this means 90 degrees to negative 180 degrees. I think it should be negative. No, it should just be pi. Give me 1 second. It should just be, yeah, pi upon 2 to pi. Simple as that. This right here is going to be 90 degrees and 90 degrees. Okay, now coming to quadrant 1. This right here, oh, I'm sweating. Oh god, yeah. Okay, so this right, yeah, so this would be from negative pi to negative pi upon 2. And you just have to convert this. This will be negative 90 degrees. No, sorry, negative 180 degrees to negative 9 degrees. Good? Alright, now I'm going to get a marker. Okay. But I can actually use this. Alright, it's fine. Okay, now coming to quadrant 3. Now look. Okay, let's just switch the markers for this one. So coming to quadrant 3, there is some marker on. Oh god. Yeah, what the hell? Bro, wait a second. Wait, what the hell is this, bro? Where's my duster at? Okay. This is supposed to be 0. Oh, I'm tripping so bad, bro. I'm tripping so bad. 0, 2. Wait, 0? Okay. Oh my god, I'm not working. Okay. 0. Okay, come on, I forgot. What was it? Yeah, wait, hold on. Yeah, pi upon 2. 0 degrees to 90 degrees. Oh my god, I'm just tripping so bad, bro. I don't know why. Okay, anyways, coming to quadrant 3. Now this would be negative pi to negative pi upon 2, where this would be negative 180 degrees to negative 9 degrees, because you have to go from the descending to the ascending order. All good? Okay, now let's go come here. This would be, this right here would be from 0, okay, 0 to negative pi upon 2. All good here? All good here? Wait, oh no, it should be negative pi upon 2 to 0. From negative pi upon 2 to 0. Let me put a bracket here. Okay, because you have to put from descent to ascending. So it's going to be negative 9 degrees to 0 degrees. All good? So this is the principal range, and I put in degrees in front of you. You can take a screenshot of this if you want. Okay? Oh my god. And the reason we put quadrant 1 after it because it's where the placement of the complex spelling is, okay? Alright, so I hope you understood this. Now, oh my god, 25 minutes. Okay, now we can finally move on to the polar form. Yes. Okay, oh god. I'm sweating. Alright. Now, let's prove the polar form, okay? So look. Through the polar form, let's draw a nice graph of the complex plane. Okay? Imaginary section, real section. Alright. Okay. Yeah. Okay? So guys, one more thing. There's one more rule I want to show you. Before I do this, just really quick. Okay, look. So look. If x is imaginary and y is real, then okay, where x, y are positive, then the argument of positive x would be it would be 90 degrees, okay, and the argument of negative x, the negative version, would be negative 90 degrees. Now this is for the positive imaginary. Now coming to the real part, argument of y, okay, would be, it will be 0 degrees. Yes, 0 degrees. And the argument of negative y, it would be 180 degrees. As explained, the reason for this is explained in the video and in the previous video I made on angle rotations a little while ago. Okay? Now because the thing is we have to use our own mind. We can't plug in this into the formula. Because tan to negative 1 of b upon a, because like for imaginary numbers it'll be undefined because the real part of an imaginary number is 0. So tan to negative 1 of b upon a would be b upon 0, which is undefined. Yeah, and for real numbers we can use the formula, but the logic I explained, it's about argument. We can also think about how many degree rotation a number gets rotated when we multiply that number by it. Understood? Okay, now coming to polar form. Time for polar form. Okay, guys, you're ready to prove the polar form. Now, our goal is to prove that a plus bi is equal to r into cos theta plus I sine theta, where r is the modulus of the complex number, and this right here is the argument of the complex number. Now let's get ready to prove. So let's take a big number, for example. Let's take 4 plus 3i right here. So this would be points would be 4, 3, AB. Okay. Now what I'm going to do is we're going to use the same logic. We're going to construct a right angle triangle right here. Just make it here. Connect the lines. Okay. Okay, everyone. Now look. In the last video, we learned that this is the hypotenuse. This is okay, and this is the opposite, and this is the adjacent. We learned this? Okay. Now, what we want to do is, we're going to rewrite this into trigonometric forms. I'm going to show you why in a bit. So let's rewrite the hypotenuse here as tan of theta. I'll use a black pen. Let's rewrite this as no theta. Where this is tan of theta. You can rewrite this in trigonometric form. And the opposite. Okay. You can rewrite this as sine theta. Sine theta. And we can write this as cos theta. Okay? Cos theta. And make sure that you know that these are also denoted as the argument, the theta symbol. But we'll find out later. Okay, look. So now, in this call, you can see that. Do you guys notice something? You see this line right here? Yeah, I'm talking about this line. This line right here. This line right here. This right here. We can also recognize this as R, the radius. And guys, there's a concept called the unit circle. I'll explain that in a bit. It's just when you draw a circle around the complex plane, then this would be the radius of the circle. That's pretty much that the explanation. Okay. Now back to drawing the polar form. What we have is R, which is the modulus. So we can rewrite this as R. Great. Now if you use our mind on trigonometry, we know that sine theta, this would be equal to A upon R, right? Take a look. Because in this case, sine would be equal to 16. We know SOH-CAH-TOA. We have to use this. So sine is equal to the opposite upon hypotenuse. Hypotenuse, opposite. Hypotenuse, opposite. Now good. Now for the cosine, it will be CAH. So cosine is equal to the adjacent over hypotenuse. So it will be the opposite. Cos theta will be equal to B upon R. Yes. Because this will be it will be equal to the opposite. Yeah, wait. So, yeah. Adjacent. This is the adjacent. B. Yeah, this is B. Yeah, this is B. This is the adjacent. This is adjacent. And this is the hypotenuse. R, as we call it, the radius. Okay, good. So now, you can continue with this. Now, what I want to do is, I want to rewrite this in terms of A and B. Okay? So what I'm going to do is, let's rewrite this. A will be equal to R into sine theta, and cos, and B will be equal to R into cos theta. Now we're just going to substitute this in A plus BR. And also this is also known as the rectangular form. Rectangular form. This A plus BI is also known as the rectangular form. This is also the standard form or rectangular form. Okay, now substitute the values. So what is A? R into sine theta plus R into cos theta of I. I can rewrite this as R sine theta plus RI sine theta. Why? Because the I is multiplying. So we can factor this. Factor the R into wait, this should be cos. R into Wait, what? Wait 1 second. Okay, wait. So r sine theta plus ri cos theta. R into sine. Wait, this should be cos. It should be cos. What the hell is wrong with me? It should be cos. It should be cos theta. This should be sine actually. This should be sine theta, okay? Now we have this expression. No, the reason because I'm making such a big mistake here. God damn it. Cos theta plus r into sine theta. Okay, now look here. R. Wait, this should actually be reversed. This should be A and this should be B. Yeah, because sine is right here, so it will be so opposite over, yeah, this over this. Okay, so now this would be r into cos theta plus I sine theta. So now look, this works for any quadrant, and now we have successfully proved the polar form. Yeah. Okay, guys. I'm very tired now. Holy shit, I'm sweating in here, bro. Okay, guys, so I think I should end it up here now. But later, so this would be r into cos theta plus I sine theta. Let's box this. R into cos theta plus I sine theta. Understand how we proved it? Okay, good. And yeah, look, if A and B is 0, you can still plug in it. You can still plug this in. You just have to find the argument, use the calculator, convert it to radians or degrees, and you're good to go. You can just plug it in. Alright guys, I think that's a lot for today's video. I have done a lot. I proved this, you know. It's pretty hectic now. Man, I'm so tired, bro. Okay, we can do this for any quadrant as well. Yeah, because sine is equal to SOH-CAH, opposite over hypotenuse. Yeah, adjacent over hypotenuse. Yeah, B is the opposite, right? Because tan of theta is equal to opposite over adjacent. Opposite over adjacent. Okay, understood. Yeah, this is why it makes sense. Okay, so now I hope you enjoyed this video proving the polar form with me. Thank you for watching with me, guys. I hope you understood more on complex numbers. And yes, we'll do De Moivre's theorem in the next video since we proved the polar form already. Okay, and we have already built on the argument. Yeah, guys. Okay, guys. So yeah, I think it should be the end for the video now. Okay. Oh, and yes, guys, the theta is equal to the argument because it also determines the angle, like tan does. Okay. So that's how I get the formula. Alright. Okay, guys. So yeah. Alright, there's also a concept called unit circle. It's just a simple concept, you know. It's the concept where we have like the modulus of a complex number. The modulus of a complex number would be 1. So all z lies in the unit circle. The unit circle is a special case where z is equal to 1 is equal to 1, negative 1, I, or negative I. We just draw a circle in between the range of these 4 numbers, and it's just a very cool fact, you know. Yeah, so this would be 4 values because the modulus of this, the distance from 0 would be 1. Okay, so I hope you understood. like and subscribe. And also, as always, stay positive. Thank you guys. See you in the next video. Whew.